Worth clarifying, I mean, we haven't talked about the virtual to physical convention that the OS uses yet. I've just, made the barest of references to it, saying that always the page directory starts at C030000, and always what turns out to be an array of page tables starts at C0000. So the fact that we see right now there's a page table entry at C02, blah, 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 it's because there's like this giant array of page tables assumed to be mapped into virtual memory. And then starting at that virtual memory, Windows uses this convention to find the page table at some offset in this array of page tables. And then because of that, then it needs to find, well, here, I'm going to put it on the board. How you can think of this looking like is, by the way, you should really write down pictures when I make them because they're helpful in the notes. How you can think of this is, in the virtual memory address space, at virtual address equal to C03000, virtual address equal to C0300000, you've got a page directory, right? And that page directory has a bunch of page directory entries in it. And at virtual address, we'll see 00000002468. You've got this array of page directory entries, or page directories, page tables rather. Sorry, page table, da da da. So Windows by convention makes sure that always it has a bunch of page tables starting at virtual memory this, and page directory starting at virtual memory this. So you can see, obviously, you're limited in how many page tables you can have, right? Because at some point, you run over the page directory. So how it handles this little virtual memory convention is, first, it does some special math in order to, when it goes and pulls out the physical address out of a page directory entry, we've got page directory entry here, which has a physical address of 3B whatever. 3B x, well, I'll just go ahead and put 000, right? So this page directory entry says at physical address 3B000, I've got some page table. The convention says, okay, based on something I know, I'm going to take that 3B and use that actually as an index into this array of page tables. And so somewhere in here, there's going to be a 3B, which gets you to C02 ... So if you do some math yourself, you may be able to figure it out. 3B times that gets you to this page table right here. And then what it does is it again pretends it's like the hardware grabs the middle 10 bits. In this case, we were looking for 8003 F and 000, right? So once it's found the page table in its little convention thing, right, what does the hardware do? The hardware takes the middle 10 bits when it's got a page table, and it offsets to get a page table entry, right? So here, it takes the middle 10 bits, split that in half, and that middle 10 bits is still 3F. But what we haven't, really emphasized thus far is the fact that that's, again, an index into the page table, which is an array of structures. Every structure is 4 bytes long. Each page table entry is a structure. So if you're at index 0, you're at page table plus 0. You're in index 1, at page table plus 4. Index 2, page table plus 8. So really what you want is 3F times 4, the size of each structure entry. So 3F times 4 equals FC. Going back up to the 1. That's why it says PTE per the virtual memory address convention is at C02000 ... FC, because the FC is this little bit right here to get you at offset FC for a very specific page table entry, and then it just writes this stuff, right? So I've already basically explained to you this entire convention, but it should be coming up here on the slides. So, but conceptually, you can think about these conventions like being You got a page directory where it always makes sure that for every given process, that virtual address always maps to some physical address of a page directory. That physical address here was 3, well, we don't know. We have to look at the CR3 to know what that physical address was. So let's check that quick. Turns out CR3 says physical address 39000. So virtual memory address here is mapped to physical address 39000, right? And that's generally kind of very close to this other physical address we found for this page table, which was 3B00 and stuff like that. But the point is, this is one virtual memory space. OS maps that to that. In the next virtual memory space, it could be mapping that exact same virtual address to physical address equals, 2011000, something like that, right? It could be anything. The point is, the OS has a bunch of physical memory, which it has a bunch of, it should be proximate, it shouldn't be way all over the place, but the point is the OS has a bunch of physical memory where it says, here's where I'm storing my page tables. I'm going to store my page directory. I'm going to store my page directory at address, 1000, 2000, 3000, up through 39,000, or something like that. Those are all the page directories I'll ever have. And it's going to say, I've got a bunch of page tables, and it'll be, maybe 3A, 3B, 3C, 3D, etc., up through wherever, right? Because we saw a page table was pointed to that 3B. So the OS reserves some chunks of physical memory and says these are a bunch of chunks for page directories, and here's a much larger amount for page tables. But then when it goes to virtual memory, it always makes sure that that stuff is mapped into known locations so that it can find it and update it. Because if it only knew the physical, and it didn't have it mapped into its virtual somewhere, the OS wouldn't be able to set flags, clear flags, change mappings, stuff like that. So the OS always has to have somewhere to find its own physical memory for these page directories, page tables. Back to me. So, like I say, and this is really where the confusion and complexity comes in when you're trying to write an operating system or you're trying to understand their operating system. It's this notion of these virtual addresses are always mapping the same location, but there are different physical locations, right? So it's this trickery. So, but I think we should now have the slides on covering this. Let's see, that was the one, I think. Should now be ready to talk about the convention, for instance. All right, so we did the Windowbug lab, we did PTE. Right, and so if you were to do PTE on a PAE mode thing, as we'll do later, that'll look completely different because it turns out those page directory entries, instead of being 4 bytes, are 8 bytes. We've got to interpret them differently. Right, and just to reiterate, there's no fixed way that virtual memory has to be mapped to physical memory. Right? The OS can do whatever it wants, right? There's no reason why this has to be C03000 per convention, right? The OS just picks whatever it wants, and each OS does typically have some convention by which they can find physical addresses in virtual memory. Or if they can't find them, then you just map it right away, right? So if you want, let's say they didn't have a convention, right? But they want to look at the page directory, or page directory for their own current process, right? Let's say they wanted to look at their own thing the same way hardware would. All they would have to do is just go ahead, well, wait a second. I think that is the case where the problem is, yes, that is the problem. You must always have some way to find and update your page directory, because otherwise, let's say I didn't know where my page directory is, but I wanted to map something physical into virtual. How would I know where to modify my page directory and a page table and stuff like that? So you at least must know where your page directory is for whatever thing is in CR3 at the moment. Or otherwise, you end up having to do that stupid thing of turn off paging completely, go out, modify your page table, turn paging back on, etc. All right, so this is the This is actually my student shirt, not my teacher shirt, but it works out okay. There we go. All right. This is a great shirt for when you're a student. All right. So here is the virtual memory to physical memory convention on Windows. Okay, so if you want to find a specific physical address, what you do is you first know that the OS will always be mapping the page directory to C0300. You just have to know that, and the OS just has to do that. If you can't find your page directory, you're hosed. So, and to a lesser extent, you need to find your page tables, but I think you could get away with not knowing where they are a priori, because then you would just modify your page directory to a specific physical address, and it can be whatever page table you want. Anyways, the way the convention works is, if you want to find a page directory entry, you start at C0300. You take the upper 10 bits of the virtual address, just like the hardware would grab the upper 10 bits, and you multiply that by the size of a page directory entry, 4 bytes. Right? So you take the top 10 bits, multiply it by 4, and that will offset you into the page directory, which is always stored at C0300, and that'll show you what the page directory entry is. Right? That's simple enough. Where it gets more complex is when you have to first find a page table before you can take those middle bits to index into the page table to find a page table entry. So how their convention works is you always start at C000. Okay, that's that bottom array of page tables. And what you do now is you take the upper 10 bits and you treat that as an index into that array of page tables. So the upper 10 bits is multiplied by the size of a page, because page tables are the size of a page directories are the size of the page. So it's like you take the upper 10 bits and you skip one page at a time, up, until you finally get to the page table you actually care about. Second, once you got the page table, it's all easy. It's all sunshine and fluff. You take the middle 10 bits and you use that as just an index, multiply it by the size of each entry. And so you take the middle 10 bits times 4, and you use that to find the actual page table entry. And this is the way by which, even once the OS has turned on paging and it can no longer directly access physical addresses, it can still find all of the page directories, page tables, and anytime it wants to map any virtual address to any physical address, it just finds a page directory, takes the top 10 bits, goes into its own page directory using this first calculation. Takes the middle 10 bits, finds a page, takes the top 10 plus the middle 10 to first find a page table and then find the index into a page table in order to find a mapping from this virtual address that they've used for the indices to a physical address. And in that way, the OS can map, any virtual address to any physical address, right? So if you want to map physical address 0 to virtual address 0, you can do it. You go at offset 0, and then you fill in the page table entry with 0, right? But if you want to map physical address to offset X, if you want to map it to 80000, same thing. You just take the top 10 bits, find your page directory entry. Take the middle 10 bits, find your page table entry, and then fill in that page table entry with physical address 0 for those top 20 bits that specify the physical address of the page, right? So you can map one page to all of memory if you want and crash subsequently. You can duplicate pages, right? Many virtual addresses can map to the same physical address. Different virtual addresses, it's saying the same thing. Different virtual addresses can map to the same physical address. I feel like there's a symmetry here, which I'm supposed to be saying, but how does that work? Many virtual to one physical, many physical to one virtual? No, that doesn't work. So it's not symmetrical. But anyways, the point is, many virtual addresses can be mapped to the same thing, and there's a name for that. Aliases, memory aliases, I think is the correct name for that. It's like you may access a bunch of different virtual addresses, but you're accessing the same physical addresses, right? So, all right, so this is the convention. Does anyone have questions on this right now? Like how this relates to that picture over there, how this relates to what the hardware is doing? Right? Anyone on the phone? Yeah, and so Corey, this was, in answer to your question that you asked before. So, is this making sense? Right, so he's saying if I'm in Windowbug and I want to translate a virtual address to a physical address, I don't even have to look at the page directory. The answer is yes. By this convention, you can just do this math, and that'll tell you where the page table entry is, right? Do the first math to get a virtual address for a page table, and use the second math to get the page table entry. And in that way, no, sorry, you don't even need to do the first math. The point is you can start with the second math, C0000, take the top 10 bits of your virtual address, use that as an index into this array of page tables, take the middle, right? So yes, it is the case that you can just, and I'll answer that in a second. It is the case that you can just skip straight to this math and find for any given virtual address, fill in this math. For any given virtual address, skip straight to this math, and then bam, you can find that page table entry. You can examine the page table entry with your knowledge of the structure of the page table entry and say the physical address for that virtual address was the top 20 bits of the page table entry with an assumed 12 bits of 0 at the bottom. So hold on, let me see that answers this question, and then I'll go through these. Right, and so the key point here is, although you can use this convention to find the physical addresses yourself, the hardware doesn't care about the convention. The hardware doesn't use the convention. The hardware is walking behind the scenes in physical addresses that you just happen to have set up with the right page. You, the OS, have just happened to set up with the right, page directory entries and page table entries, right? So the hardware doesn't use this little heuristic about C zeros and whatever. The hardware just says, whatever CR3 is, I go to that physical address. Whatever's in there, I go to that physical address. Whatever's in there, I go to that physical address. Right? So hardware doesn't care. Yes, Reed?
I think you answered it. Thank you.
Okay.
It seems like you still have to check the page data entry no matter what, in case you had the big pages.
Yes, potentially. So he was making the point of, do you still have to check the page directory entry in case you have big pages? And yes, right. We keep saying about big pages, but we haven't actually, shown the information for them. But yes, if we know that we know that a virtual memory address could translate instead of from page directory to page table to page, it could just go straight up page directory to page, giant page, right? And that's why we have to actually, if you're wanting to be rigorous about it, you can't just assume you're walking to a page table. You've got to check whether or not you actually are going to a page table by first checking if you're going to a giant page. All right, thanks, Bill. And so does that also further clarify, Corey? So there's one more question. Will the physical address in the page table convention, C000 whatever, change per process? I don't believe that's the case. I believe it's the case that in every single page directory, page tables, or for every single page directory and the single page table which corresponds to the right offsets in order to do the C000 or C03000, for every single virtual memory space, the OS is going to set in that convention so that you always, no matter what virtual memory space, you can assume if you do this offset and that offset, it maps back around to the same physical address that the page directory was. And we'll kind of see that once I have a little picture of that, I'll show that. And then it may be too much for this class, but I will talk a little bit about how if you were in kernel space, you could read all of the memory for those user space processes by pretending that you're the hardware and looking at the page directories and page tables that the OS's data structures say relate to calc.exe and notepad.exe. You could think like, if I were the hardware, and this page directory was in effect, and these page tables were in effect, what virtual memory space in calc.exe would translate through those tables in order to get a physical address. And then you can kind of read some physical addresses from user space, but they may be paged out. right? So you've still got all those issues. So. All right. All right, so this was just one example by hand. I'm not going to do it on the board since we'll probably taken us back a little ways. If you have the GDT and you are pretending that you were the OS, not the hardware now, right? You were the OS and you wanted to just find out for this GDT entry, where in physical memory is it stored, under the assumption that it's not stored on some giant page, right? Well, even under the assumption, if it is stored on a giant page, you just need to pay attention to what's actually in the PDE before you move on to the second calculation. So in binary, this is the grouping, right? This is the binary for that thing. And we said you take the top 10 bits, which in this case, although it was, 800, right? You take the top 10 bits and you group it up, it turns out to be hex 200. You take the middle bits, those are still hex 3F. And the bottom bits, bottom 12 are just 0. So we said that the math for the PDE was start from the assumption of I always have my page directory at C030000. Take the index into this array of data structures, multiply it by the size of the data structures, the 4, right? So hex 200 times 4, and you get C0300800. If you go back to WinDebug, you'll see that's the address that PTE calculated, right? Second, so now the point is you could go to that virtual memory address, and that's where you would see the 4-byte data structure, which is the page directory entry. Then if you wanted to find a page table entry, because it looks like this thing translates to a page table, not a giant page, you just go to C0000. You'd again take the top 10 bits, and this is sort of the index into that array of page tables, right? So use that times the size of a page, hex 1000. And that's what got us up to this C02000, right? And then you add that to the middle 10 bits, which was 3F, times the size of the data structures that you're offsetting into the page table entry, right? 3F times 4 equals FC. And that's why this is the final virtual address where the page table entry is. And you can go there and look and find the actual physical address and all that stuff. Anyone have any questions on this? Pretty straightforward on the math here. All right, so this is the picture I wanted to say. This is, if you're tracking everything so far, this is kind of how you can think of the memory convention. In order to make it so that every page directory and the single page table entry associated with that directory in every virtual memory space always maps back to the page directory, it's got this sort of looping thing here. And how it works is the OS must think like, if I were going to be in that virtual memory space of this new page directory, how would I translate that virtual memory space back to the physical address, which I know is my own page directory? Right, so you got some page directory. It is whatever it is. Let's say it's 39000, right? Physical address 39000. It wants 3900 or 3A00 or 3B00. It wants any of those page directory physical addresses to always, in every single page directory, to map to C03000. So how does it do that? It takes this C03000, breaks up the top 10 bits. It turns out, if you take the top 10 bits, it's actually indexed hex 300. So they go into the physical address, or they go to the physical address. The confusing thing here is, right, if you're in the context of one page directory, let's say you're in the kernel context, but you're trying to set up you just started calc.exe, and you're trying to set up its virtual memory space, right? And for this new virtual memory space, which you're going to assign to calc.exe, you want to make sure that in that virtual memory space, your convention still holds, right? So you went to your pool, you pulled out, 3A000. You say 3A00, that's what I'm going to use as the page directory for my next process, right? Calc.exe. The thing is, that's again a physical address. So you need to first, in your current context, map that physical address to some virtual address so that you can, twiddle the bits in there in order to set stuff up. So first, the kernel technically has to map that physical address into its own context so that it can edit it. But now, assuming that the kernel can edit the page directory, which is setting up for the next process, what it does is it wants to enforce this convention, so it goes index hex 300 into whatever virtual address it's mapped that physical address to, index hex 300, fill in a new page table. It goes out to its collection of free physical things and it says, okay, 3B 000. That's my next page table. At index, hex 300 into this page directory, I will fill in 3B000 for the next thing, right? We're saying right now the new thing is 3A. The new page table is 3B. Right? So it fills in physical address 3B in the page directory entry. And, again, it has to at least map that one page table into virtual memory somewhere so that it can edit it. And what it does is then it edits it so that index hex 300 into that page table maps around to physical address 3A. Right? So let me go to the board and show this with literal addresses, like that picture there. Kind of makes a little more sense with picture, right? So ignoring the fact that the Windows has to map each of these, page directory, one page table. It has to map them somewhere in memory to edit them, right, in its current context. But it's editing them thinking, what will things be like when I set these as the current context, right? So all it really does is somewhere it has the ability to edit a new, right? It has a new thing, which this is physical memory. Physical equal to 3A000, right? Physical memory 0, it's saying, I'm going to use that physical memory as a new page directory. Right? So it goes index hex 300 in here. Hex 300. And for this page directory entry, it goes ahead and it sets 3B, assumed 000 to the bottom. Right? And that's the page table. Okay, so we got that there. That's is equals 3B000, right? And so it sets that index 300 to 3B so that it points to that page table, right? And then it goes to index 300 here, and it sets that one to 3A. So that's why it's looping back around. It says for the translation, which I know the hardware would do for the virtual memory address C0300, which is index 300, what would essentially happen is at some point it's going to say, okay, calc.exe go. When it does that, it says CR3 equals that new page directory, right? That's the virtual memory space from my new thing, right? And in that virtual memory space, if the hardware does, if the hardware tries to, if in that virtual memory space someone asked for that virtual memory address, right, the hardware would translate it by doing index 300, which would say, oh yeah, my page table is at 3B. Index 300 and say, oh yeah, this page is actually at 3A, right? So this is normally supposed to point to some new page which handles stuff for that virtual address. But it turns out that just wraps onto there. And that way, C000, and that way over here on, virtual address land, C03000 maps to physical address 3A. Because you take that, you break it up, you get bam, 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 right? And that's how you can edit your own page directory by convention in every process. The OS has to always set that up. And, that's why it's this address, right? 300, 300, nice and simple. And bam, set them up, loop them over. All right, any questions on that? I know that's, again, one of the crazy bits, but really, as far as you're concerned, most of the time, since you're not writing the OS, and you're not trying to, until you're writing your own OS and having to deal with this paging yourself, right? All you need to think about are these simple calculations, right? For any physical address I want to map into my current space, right? If your kernel module, there's just one big virtual memory space for every kernel module and the kernel itself, right? So if you've got some free memory somewhere, if you want to go examine physical addresses, you just say, okay, where's free? Walk the current page directory, watch the current page table, find some translation for which the page direct table entry has present equal to 0 and no data structure in the top bits. And you now know that virtual address I can map willy-nilly. I can modify the OS's things, right? You're not supposed to, but you can, right, now that you know this stuff. So yeah, you're definitely not supposed to do this. But the point is, if you find some virtual memory space free, you can map it to whatever physical address you want and examine whatever's at that physical address. So if that physical address is a page directory, so be it. If that physical address is a chunk of calc.exe, so be it. If it's a chunk of notepad.exe, you can see all that from within the kernel, as long as you understand, first of all, how do you find the page directories and page tables associated, right? You really only need the page directory, right? If you find the page directory associated with calc.exe, it'll tell you where all the page tables are. They're in the page directory entries, right? It'll say 3B and 3C and 3D and stuff like that, right? So you can go find all of those, and you can map those into different things. So just like that, you as a kernel module really only need two things, well, three things. You need to map, you find calc.exe's page directory, map it into some free space. And then find whatever virtual memory address you're trying to translate, map it into, your second free space, which is your page table, right? So you're reserving one spot for page directory, one spot for page table, and one spot for the actual final terminal physical address, which corresponds to, calc.exe's code section or something. And that's basically how, from kernel space, you can do user space measurement and inspection and stuff like that for those of us who care about memory integrity measurement. Yeah, that's why it's complex. All right, so let's see where we are relative. We're gonna probably run out of time. Oh well. So where we are relative to things, this is just now coming back around to talk about those page faults again. If either of the PDE or PTE has a not present set, right, present is set to 0, then you get a page fault, right? So that's interrupt 14. We haven't seen interrupts yet, but this is just a tie. The reason why we're doing these things in order, right? We had segmentation. Segmentation directly precedes and relates to linear addresses for virtual memory, right? When we've got virtual memory, one example of where it talks about interrupts is you're trying to access something that simply isn't there. It's been paged out. You're trying to access read-only memory as right. You get a page fault, interrupt 14. When a page fault occurs, the OS gets to choose, what it wants to do about it, right? The OS sets a handler for that, and the OS has to decide in any given case what it wants to do about it. There's different cases, such as the most common we've talked about thus far is swapping out to disk, right? Paging out to disk, we call it swapping, to avoid the overloaded term. So when something's swapped out to disk, as we've already said multiple times, the OS says, I don't have any more physical memory. I need to free something up that says that, hey, your virtual address hasn't been used in a while, right? Your physical address, I'm going to take that memory out of your physical address, copy it off to disk, and reuse that physical address for some other page directory entry, page table entry thing that it points at, some other frame. So when the page fault kicks off, the OS can say, okay, well, I'm going to go walk the page tables myself and see what was the nature of this change. Is it because present bit was set to 0? If so, then I'm going to check for that data structure. If not, was it, well, it has some other methods, and actually now that I think about it, I don't know how it's actually determining. I'll have to look at the interrupt 14 in a second here. There may be an error code which helps the OS figure out what just happened. Because otherwise, how would the OS know, just based on looking at flags in the page directory entries, how would the OS actually know whether or not it was like a read-only fault or something like that, right? Or how would it know whether or not it was a user supervisor thing, something like that. All right, and since Dave's here, I guess we're going to take lunch at 11:30. And so one case is stuff is paged out to disk, and the OS has to figure out if this is paged out to disk and someone's trying to access it right now, then it'll go ahead and pull it back into memory silently and just let the process continue on, and it never knew anything happened, right? Trying to be transparent in that way. Another case where it's trying to be transparent is stack growth, right? So we said stack addresses grow towards low memory, but it's not going to just allocate a ton of memory that you may never use if your stack's just adding one, subtracting one, adding one, subtracting one, right? So how the OS does it is it starts you off with a page of stack space. And after that, if you start growing, your stack keeps getting bigger, and when it crosses a page boundary, then you get a page fault because that next virtual memory address space for that next, frame worth of memory is not mapped, right? The OS gives you one page of virtual to physical translation, and if you grow off the bottom of that page, then you get a page fault, and the OS says, okay, where did that page fault occur? Oh, it looks like it's on the boundary of some stack space that I set up. I'll go ahead and allocate a new physical frame to that virtual address of the next area and go ahead and let the thing continue. So similarly, let's say you've got some recursive code that's, massively growing the stack and destroying the stack. It's all silent to you, the fact that the thing has kicked off these hardware faults and saying, hey, you don't really have that virtual memory address. Oh, hey, I'll just fill it back in because I need to let your stack just automatically grow. At some point, it's going to grow to the point where it says, this far and no farther. But that's usually, for instance, where, memory regions of heap versus stack start bumping up against each other, right? Because heap grows up, stack grows down, right? And in some cases, it may, let those things grow farther or not. They're not going to like necessarily have a hard-coded, like stack may be this size max, heap may be this size max. Maybe they want that to be a little soft, and they can let this, heap grow up big. But at some point, if your stack ever grows to the point where it hits some active heap data, that's the point at which it says, this far and no further. All right. The other one we talked about was copy on write, right? If the OS marks something as shared, right, it's going to map it into two different virtual address spaces, so it's sharing it. But if in reality it doesn't want each of those things to actually be able to write to it, then it marks it as read-only. If someone does a write operation, it catches a page fault, and then it goes ahead and says, okay, well, that was shared, and I still want you to be able to see whatever version you changed, calc.exe. So I will copy the existing frame of physical memory into a new frame of physical memory and update your virtual to physical thing so that you get the copy that you just modified. Right? So those are all recoverable ones. But then you've got these other things like, linear to physical translation is simply not valid. If you go to 0, and if you end up like, hey, that page table entry is straight up zeros, right? The OS can do nothing about that. You're accessing memory which you never should have, right? If your program was programmed correctly, you wouldn't have had that null pointer dereference. That's your problem, not the OS's. It kills you. You got to go debug it. Right? And then finally, that other thing of user space code accessing supervisor, for instance, that's an uncoverable thing. So the OS needs to know that's what just happened, but then it can go ahead and kill that process saying, you're trying to access the code. Or it may, as we said before, it may pass down a general fault to the program to say, go ahead and recover this if you can, but I'm not sure on that. All right, good. Good leaving off place. Thus far, we've covered all of the 32 to 32 4 kilobyte pages. Next, we already made reference to this, but when you deal with 4 megabyte pages, which would essentially be all the space that any given page table could have translated to, right? So you're cutting out the middleman, and you're saying, go directly to 4 megabyte space. This is what we're going to see, and that's when the global bit starts to matter on the page directory, for instance. So we'll see this when we get back. Anyone have any questions?